Hello everybody. Let us try to take one more problem on mesh analysis, which is in continuation with problem number 1, which was a very simple problem that we had taken up earlier. In my first video, I had taken up a simple, very elementary problem on mesh analysis. Now this is another simple one wherein we are expected to write mesh equations for the circuit shown in figure below. Okay, that's how the problem goes. So as you can see in this particular problem, we can clearly identify 3 meshes, and in the problem itself mesh currents have been given. They are clockwise currents. That is standard practice to assume clockwise currents in meshes. Okay, independent 3 meshes we can clearly identify, and 3 mesh currents have been shown to be flowing in the clockwise direction in each and every mesh. Alright, now how to go about writing the mesh equations. Now in this problem, let us try to write the mesh equations by inspection, not by first principle. Alright, so how to write the mesh equations by first principle, let us try to see in this problem, so that this becomes easy for us, or we get used to the method of writing mesh equations by inspection. Okay, so the solution goes this way. Solution is that we will first take up the mesh 1. This is our mesh 1. I will take a different color and identify. This is mesh 1. Okay, this portion is our mesh 1. This pane is our mesh 1. So we'll try to write an equation for the mesh 1. So our first element in the mesh equation is the sum of all the impedances contained in the first mesh. So here this first mesh has got some real parts and some imaginary parts. So real part is the resistive part of the impedance, and the imaginary part is either inductive reactance or capacitive reactance. We know inductive reactance is represented by J omega L. This is the way we represent inductive reactance, and capacitive reactance Xc is represented by minus J divided by omega C. Okay, so this is how we represent the reactances, or in other words, it is J something something, and this is minus J something something. So that's how we represent. All right. So now, how to write the equations? You cannot arithmetically add real and imaginary part, so to take it as a complex number. So if we look at mesh 1, we can see 1 ohm resistance here, 2 ohm resistance here, another 1 ohm resistance here. They are all real parts which can be added up. So that comes out to be 4 ohms. Plus we have to now collect the imaginary parts. What are the imaginary parts? We have one here, J3, another we have one here, that is J2. That adds up to J5. 4 plus J5 into I1. So this is Z11. We have to bear it in mind. Okay, we need not write it, but then we have to bear it in mind. Now, how to write the second one? So what is the second element in the equation? See, if you can see, this equation will be a 3 by 3, 3 equations and 3 unknowns. Okay, so if you write it in a matrix form, these equations will appear as, this is the impedance matrix will appear as 3 by 3 matrix. We will come to that later, you will realize it subsequently. However, let us try to write the second element. What is our second element? If we remember, we indicate the second element. I have explained it in the first video. You can look into my first video if you do not understand this. Second impedance is represented as impedance common between the first and the second mesh. So where is our second mesh? We recognize the second mesh as this mesh, where we have I2 current to be flowing in the clockwise direction. As I told you, mesh is the smallest closed path in any network. Alright. Now we will try to write this Z12. What is it that is common between mesh 1 and mesh 2 is something that we need to identify. So obviously this 2 ohm is something that is common between these two meshes, mesh 1 and mesh 2. So we try to take that particular element with a negative sign, minus, we take the impedance, that is 2, in case only the resistance here in this case, it is 2 into I2. Alright. Now, we have to write the third element. What is the third element? Third element is identified as Z13. What is common between the first and the third mesh? That means it is this and this. What is common between this and this? What is the common branch between that and that? First mesh and the third mesh. That again has to be taken with a negative sign. So that will be minus of. So you have to take the impedance. What is that impedance? You have 1 ohm is the real part, J3 is the reactance part or the imaginary part. It is taken as 1 plus J3. We have to put brackets, otherwise we may mess it up, into I3 equal to the source of EMF, which again in the clockwise direction is rise in potential. This is 5. Alright. This is our first equation. Okay, see, we wrote one equation by inspection. How to write the second equation? How do we identify the second equation? If you look at the second equation is written for the mesh number 2. Okay, so how to write the mesh number 2 equation? The first element in the second equation is remembered as Z21, that is impedance common between the second and the first. The first subscript indicates the mesh of current importance, or you are writing equation for that mesh. Okay, this is x2, I mean 2 will indicate we writing it for second mesh, and this subscript indicates the element that is common between 2 and 1, mesh 2 and mesh 1. Okay, so how to find out that? So what is common between 1 and 2 is same as the thing that is common between 2 and 1. It is that simple. So obviously what we get here is this is the element that is common between this mesh and this mesh. Rather 1 and 2, right? I'm sorry, 1 and 2. We need to write 1 and 2 first. This is my second mesh and this is my first mesh. This is the element that is common, 2 ohm. So what do we write is, it is minus 2 into I1. Okay, that is taken with a negative sign. Now, the second element is identified as Z22. So the sum of the impedances contained in the second mesh alone. That is, you have one 2 ohm resistance and you have one 3 ohm resistance, and minus J2. This is the reactance, this is the real part. Impedance is expressed as a complex number, A plus JB. This is how we represent the impedance, plus or minus for that matter. Okay, so how to write now? We can add this 2 and 3 and that becomes 5. So now I take it with a plus sign because it is the self impedance. This is 5 minus J2. This has to be multiplied with I2. Okay. Now, what is the third element? Third element is what is common between the second and the third mesh. That has to be taken with a negative sign. So I'll put the negative sign first. What is common between mesh 2 and this is my mesh 3? Where is my mesh 3? This is my mesh 3. What is common between mesh 2 and mesh 3? It is this particular element that is common between mesh 2 and mesh 3, minus J2. But that the impedance itself is minus J2. So I have to take it as minus J2 into I3. And that is 0. There is no source of impedance. So this is my second equation. Alright. Okay. Now we go to the third equation. How to write the third equation? So here in the third equation, the first element is identified as impedance common between the third mesh and the first mesh, that is taken with a negative sign. Okay, the third mesh and the second mesh is taken with a negative sign. Minus, what is common between third and first? It is J3. So minus J3 and into I1. Alright, sorry, 1 minus J3, 1 is also there. 1 minus J3 into I1. Okay, now what is common between the second and the third mesh? That has to be taken with a negative sign. So that is minus, the thing that is common between the second and mesh is minus J2 into I2. The third element is the sum of the impedances contained in that particular mesh itself. So what will that be? If I can look at that, I will see, I'll sum it up here on this side, or I'll sum it up here and then erase. Okay, so it is, I'll go in the clockwise direction, minus J2, okay, plus 1 plus J1 plus J3 plus 1. I have taken from top left corner, this top left corner, go in the clockwise direction. I have added all the impedances. Okay, so how much is that going to be? 1 and 1, that's all, that is 2. And how many J's are there? This is J3, this is J1, both are plus, that is J4, minus J2 is again, that leaves that with J2. So this addition would be 2 plus J2. Okay, now I will remove this entire thing I erase, and I'll put it back. I'll write this as 2 plus J2 into I3. Is there any source of EMF? No, that will be 0. See, we are able to write the equations by inspection. This is the best part of mesh analysis. If we have to do it by KCL KVL method, we, instead of mesh currents, we assume branch currents, and the number of currents would be equal to the number of branches, and then you will have to alternatively apply KCL and KVL, and then try to solve the equations. That is little complicated. So instead of branch currents, in mesh analysis method, we assume mesh currents, and mesh currents are assumed to be clockwise currents typically. Okay, you can assume even anti-clockwise currents, but then if the situation demands, we even assume anti-clockwise currents. We can take up a problem or two wherein we deviate from this convention. Let us see how that works out. That's going to be interesting. Now these are the equations. Isn't this simple? Isn't this method appealing, attractive? Now we will try to put the same equations in what we call as vector matrix form. This is another form of representing simultaneous equations. Just for our interest, I will put the above equations, the above mesh equations in what we call as vector matrix form. Can the above mesh equations in vector matrix form if we put it like this, we write the matrix in this manner: I matrix, rather I'll take the Z matrix only. I'll take the matrix Z. The equation becomes like this: matrix Z into vector I equal to V. It takes this form. Okay, we will put the equations. 1, 2, 3. What we do is we try to pick the impedances. We try to put these impedances, this with their signs, this with their signs, or the coefficient of I1, I2, I3 from the 3 equations we take, and then make the impedance matrix. Okay, so our impedance matrix has got the first row as the first coefficient of I1 that is 4 plus J5, coefficient of I2 minus 2, coefficient of I3 minus 1 plus J3. Alright, so we arrange it in rows. Now the second equation, the coefficient of I1 is minus 2, coefficient of I2 5 minus J2, coefficient of I3 is J2. I have converted this, I have taken the product minus into minus, that becomes plus J2. Okay, here again it is, skip the minus sign here, minus 1 minus J3, sorry, this is 1, you have plus J3, I'm sorry, 1 plus J3, okay, this is 1 plus J3, okay, 1 plus J3, and this is J2, this is 2 plus J2. So a complex number is preferable to be included within brackets. Okay, it's a good practice to include to put the complex number within parentheses. Okay, so this particular matrix is what we call as impedance matrix or Z matrix. Alright, now this into, what are the currents? We have the currents to be I1, I2, I3. This is a vector. This is equal to, we'll try to put everything, all the voltages here. This is 5, 0, 0. So this matrix is written like this. This is what we call as vector matrix form. Writing the equation in what we call as vector matrix form. Okay, here in this form, if you can identify, this is your impedance matrix. Impedance matrix, and this is your current vector, and this is our voltage vector. These are all column vectors, and this is a 3 by 3 matrix. Impedance in this particular problem is a 3 by 3 matrix. 3 by 3, and this is 3 rows and 1 column. The resultant is again going to be 3 rows and 1 column. It is this A by B multiplied with B by C is equal to B by C. That's how you get the multiplication of matrices. Alright. So what I am trying to tell you is, this is how we identify the various components of the equation. There is an interesting thing to be observed. In this impedance matrix, we can easily identify some important things. What are those important things? If you observe this matrix, you can see that this matrix has got Z12 equal to Z21, which is equal to minus 2. Okay, this is equal to minus 2. So this is something that is interesting. And then this element, that is minus 2, this we are talking about. Now how do we identify this element? Minus of 1 plus J3. This is our Z13, the first element, first row, third column, Z13. This is equal to Z31. That is the third row and first column, this one. Both are same, minus of 1 plus J3. Even if we do mistake, we can always cross check whether we are getting it correct or not. You have to get them to be this way. Okay, and now we come to another element, the second row and the third element, third column. Okay, impedance of the second row, this is the second row, and this is the third column. This one we are talking about J2. Okay. All right. Second row and third column, that is Z32. This is J2. Okay. Now the remaining are all independent ones. Like your Z11 is unique, Z22 is unique, and Z23 is unique. But if you can see, these two and this one are the same. This can be seen to be true. Okay. So this is another problem which has helped us understand the method of writing the mesh equations by inspection. By inspection we mean by looking at the network. See how quickly we were able to write these equations. With practice you can write it in no time. Okay, with practice you can write these equations within no time. Okay, more problems will make us understand things better. We will slowly move on to few more problems as to how to write the mesh equations. Okay, so in all the videos, in most of the videos I am covering only the independent sources. Let us see, if time permits, I will make some videos on dependent sources and then upload. Happy learning. See you next week in the next video. Bye till then.